In this video, I'll be discussing the content checkpoint for the momentum conservation model. So the first thing that you should do is look over this list of skills that you have to have going into this exam, because there are a few different concepts here you want to make sure that you're familiar with. Those equations on the bottom, of course, as well, pretty important. So just make sure as you go into it that you've looked over this list and that those things make sense to you and that they're skills that you think that you have. Okay, so the first section of this content checkpoint is all about concepts, and I will discuss each of these questions, and hopefully after I go through them, they should make some pretty good sense to you. If they don't make any sense, make sure that you come in and ask, because there are going to be similar questions on the exam, and if you don't know what's going on in here, you probably won't know there either. So the first question here, it says a rubber ball is traveling forward with a momentum of 5 kilograms per second. It hits a block which has twice its mass. The ball bounces backwards and travels with the same speed but in the opposite direction. What is the change of momentum for the block, and how do you know? So there's some key things here. First of all, the rubber ball had an initial momentum of 5 kilograms per second, and then we know that it bounced backwards and it traveled in with the same speed but in the opposite direction. All right, and so what this tells us is for the ball, the original momentum, which I'll call Pi, equals 5 kilograms per second. Or the final momentum equals, it's going the same speed but in the opposite direction, so negative 5 kilograms per second. So what we know here is the changed momentum for the ball equals negative 10 kilograms per second, because it went from 5 to negative 5. That's a change of 10, and it goes down. All right, so then what we know for the block is that it has a change of 10 kilograms per second, because it has to gain whatever the ball lost. And so if the ball lost 10 kilograms per second of momentum, by the law of conservation of momentum, the block must have gained that momentum. All right, so that's how that one works. For number 2, it says a rubber ball is traveling forward with a velocity of 30 meters per second. It hits a block with twice the mass. After the collision, the ball is at rest. What is the final velocity of the block, and how do you know? So here's the case in this one. We've got a ball, and it's traveling 30 meters per second. All right, and then it hits a block that has twice the mass, and then it says at the end, the ball's at rest. And so what's happened here is the ball has transferred all of its momentum to the block. All right, the ball transferred all of its momentum to the block because the ball doesn't have any momentum in the end. So the final momentum for the block is equal to the original momentum that the ball had. All right, and the mass of the block is twice as much. And so here's kind of what we have. I'll explain this with an F chart. Originally, we had the ball, which was going 30 meters per second, and it had a mass of m. I don't know what it was, but it was some mass, right? And then we had the block there, which has a mass of 2m, and it wasn't going anywhere. All right, for the final situation, what we've got is the ball, which has that mass of m, is at rest. All right, and then the block, which has a mass of 2m, is moving. Now, because the mass has doubled and we have the same momentum, the velocity needs to be 15 meters per second. It should be half as much. If we doubled the mass, we need to cut the velocity in half in order to preserve the same amount of momentum that the ball had. Because if that same momentum is distributed over twice as much mass, it has half the velocity. So in this case, the velocity equals 15 meters per second. For question 3 here, we've got a train car. This is traveling forward. It has a momentum of 20,000 kilogram meters per second. It strikes another train car which is at rest. Both cars are moving forward after the collision, but they are not stuck together. Is the final momentum of the second car more than, less than, or equal to 20,000 kilogram meters per second, and how do you know? So here's what we've got. Again, it's going to be a similar sort of situation where if you think initially, right, we've got a train car that is traveling forward and another train car that is at rest. All right, and the area here, the momentum, is 20,000 kilogram meters per second. All right, and so what we know here is that the total momentum is equal to 20,000 kilogram meters per second. All right, because of the law of conservation of momentum, we know that momentum has to be conserved. All right, and so in this case, then, when we have two objects moving, all right, the two momentums that they have, we'll call this P1 and P2, those two momentums. We know that P1 and P2 together has to equal 20,000. Because the law of conservation of momentum says that the total momentum here has to equal the same thing on both sides. All right? Which means if the two momentums add together to give you 20,000 kilogram meters per second, and we know that both cars are moving, that neither of them has the full 20,000 kilogram meters per second. It's split in between them. All right? So we know that P final, in this case for that second car, is less than 20,000. Because that 20,000 kilogram meters per second is split between both cars. Okay, so question number 4 is a similar problem, but it's got a slightly different tilt on it. What it says here is a train is traveling forward with a momentum of 20,000 kilograms meters per second, and it strikes another car which is at rest. And it says after the collision, the first car is moving backward. Is the final momentum of the second car less than, more than, or equal to 20,000 kilogram meters per second? So it's a similar situation here, right? We've got train cars here. In our initial situation, there's only one moving. It's got 20,000 kilogram meters per second. All right, we've got another one that is at rest. It's not moving. All right, and so we know that the total momentum, in this case, again, equals 20,000 kilogram meters per second. Okay? So then if we make the final situation here, that momentum needs to be maintained, the law of conservation of momentum. We know that we've got one car going in the negative direction, and the other car then would be going in the positive direction. I'm going to call this momentum P1 and this momentum P2. All right, and what we know, since P1 is in the negative direction, we know that P2 minus P1 equals 20,000 kilogram meters per second. And so in this one, you're taking the difference rather than in the other one that you were taking the sum. And so if we know that the second momentum minus something equals 20,000 kilogram meters per second, then hopefully it stands to reason that P2 is going to be more than 20,000. If P1 was 1,000, P2 would have to be 21,000. If P1 was 5,000, P2 would have to be 25,000. All right, so in this case, we know that P2, all right, is greater than 20,000 because it has to make up for the fact that P1, or the train car number 1, has a negative momentum. Okay, on to problem number 5. This one says a billiard ball and a bowling ball are dropped from the top of a high building, assuming that they have not hit the ground. which object has more momentum 5 seconds later, and how do you know? Well, the first thing to notice here is that they would have the same velocity because they're falling under free fall motion. All right? So okay, so they have the same velocity because they're in free fall. All right? However, the bowling ball is going to have more mass, so the bowling ball is going to have more momentum. All right, moving on to the next question here. It says, two absent-minded skateboarders are headed toward each other. The first has a mass of 80 kilograms and the second has a mass of 60 kilograms. When they collide, which experiences the greater force? Which experiences the greater change in velocity? Which experiences the greater change in momentum? In each of these cases, consider the magnitude or the absolute value, not the direction of the vectors. So this one, a couple things. First of all, they have the same force. Okay, and the reason for this is Newton's third law. Which says that if two objects are pushing against each other, they're pushing with the same force. You can't have one pushing more on the other one. They also have the same change in momentum. Okay, in this case, they have the same change in momentum because the law of conservation of momentum says that whatever momentum one of them loses, the other one gains. So this one is the law of conservation of momentum. In this last case, though, with the velocity, the smaller boy has a larger change in velocity. All right? So the 60 kilogram skateboarder experiences the larger change in velocity. And the reason for this is because he's got a smaller mass and the same change in momentum, so he's going to have a larger change in velocity. If you've got a change in momentum and it's the same as the change in momentum of something that's larger, the smaller object is always going to be more impacted by that change in momentum. I made in class the analogy of a semi-trailer and a mosquito hitting each other and which one it affects more, and it's always going to affect the smaller one more. So they have the same change in momentum, but affects the 60 kilogram skater more because he has less mass. Okay. Number 7. It says an object experiences an unbalanced force over a period of time. Object B has twice the mass but experiences the same force over the same period of time. Which one has a greater change in momentum, and how do you know? Well, we know here, I've talked about force and time, which should hopefully clue you into thinking about impulse. And so we know that impulse is equal to our change in momentum, okay, which equals an unbalanced force times time. Okay, and so it's the same force and the same time, therefore it has the same change in momentum, because I said both of them experience the same force over the same amount of time. So in cases of impulse, mass does not matter, all right, because we're talking about a change in momentum, all right. the one that has the smaller mass is going to have a greater change in velocity because of what we had talked about with that last problem here, but they're going to have the same change in momentum, right? Because it's the same force over the same amount of time. Okay, on to section B. Section B is some different problems that we've got here. And so this first one involves a bullet which is shot into a block of wood. And I said that the bullet remains inside of the block of wood after the collision, so they kind of combine into one object. And I want to know the final velocity of both after the collision. And so what we do here is you always start by making your if chart. All right, this is a velocity versus mass chart. All right, we've got the bullet moving originally, but the block of wood is at rest. And so what I'll do here is I'll say that we've got this bullet. It has a mass of 0.01 kilograms because it is 10 grams, so 0.01 kilograms. And we know that the velocity here is equal to 100 meters per second. All right, so it's traveling 100 meters per second. And then we've got the block there that's not going anywhere. All right, and it's got 1 kilogram of its mass, but it's got nothing in terms of its momentum. If we calculate the momentum here of the bullet, you take 100 times 0.01, and you get that it has 1 kilogram meter per second of momentum, which means that the total momentum in this situation is equal to 1 kilogram meter per second because there's only one object here and it has 1 kilogram meter per second of momentum. There's only one object moving. So we know that on the other side, when we make our final thing, that because momentum is conserved, that the total momentum after the collision is going to also equal 1 kilogram meter per second. The next thing you have to think about is what's moving in the end. I said we kind of only have one object here, right? We've got the block and the bullet kind of fused together into one object. And so I'm going to assume that it's moving here in the positive direction then, because we know that momentum is positive. It has a mass of 1.01 kilograms because it is the mass of the bullet plus the block. We know that the momentum here then, because there's just one object, has to be the total momentum is 1 kilogram meter per second. All right, and then we can calculate the velocity by taking the momentum and dividing it by the mass. And when we do that, we get 0.99 meters per second. All right, and so that is the answer there. The final velocity of both objects is 0.99 meters per second. So problem number 2, we've got a train car, and it says it's traveling with a mass, a train car has a mass of 10,000 kilograms. It's traveling forward on a track, velocity of 10 meters per second. It collides with another train car, which is moving forward with a velocity of 4 meters per second. After the collision, the cars are traveling forward at 6 meters per second and 8 meters per second, respectively. What is the mass of the second car? So this one's actually really interesting because we don't know the mass of one of the cars. And so it makes it a little bit more confusing the way that we're going to do it, but we still know that momentum has to be conserved. And so here's my recommendation for how you should do this problem. We've got one car that has a mass of 10,000 kilograms. All right, and it's going a speed of 10 meters per second. All right. So we actually know from that one, since it's 10,000 kilograms and it's going 10 meters per second, we know that the area of this is going to be 100,000 kilogram meters per second. All right, then we have, going slower, this other car that has an unknown mass. And we know that it's going 4 meters per second. So I'm just going to call this M for our unknown mass. All right, and we know that it is going here 4 meters per second. Okay, and so if I find the area of this one, I just take base times height. It's a rectangle, so it's going to be 4m. All right, 4 times whatever my mass is. Then I go to the final situation, and I can do something similar. All right, I know that the first train car is going 6 meters per second, and the second one is going 8 meters per second. So what I'll do here is I'll say this one here, which has a mass of 10,000 kilograms again, is going 6 meters per second. All right, and from that, I can figure out again its momentum. All right, it is 6 times 10,000, which is 60,000 kilogram meters per second. The other car is going faster. It's going here at something like 8 meters per second. And we don't know what its mass is, so again, I'm just going to call it m. It's going to be the same mass as what it was originally. And if I think about what the area of this rectangle would be, then it's going to be 8 times whatever my mass is. And then the last crucial step to this is remembering that momentum is conserved. All right, so the total momentum on the left-hand side needs to be the total momentum on the right-hand side. And if you do that, then we can add up here. We know 100,000 plus 4m has to equal the momentum on the other side, the total momentum, which is 60,000 plus 8m. All right, and then if we just do a little bit of algebraic simplification here, we end up subtract 4m from both sides, subtract 60,000 from both sides, and what we end up with is 40,000 equals 4m. All right, and then if you solve that, you should get that m equals 10,000 kilograms. So as a coincidence, this second car ended up having a mass of 10,000 kilograms as well. Okay, this last problem here is an impulse problem. So what we'll be doing here is we'll first be doing an impulse calculation. We'll use that for our initial graph, and then we'll talk about our final graph. So we've got a rubber ball placed in a slingshot. It says it's launched with an average unbalanced force of 20 newtons per 0.1 seconds. All right, so the first thing I'll do is I'll do a change in momentum equals F ut, unbalanced force times time. When we do this, we get 20 newtons times 0.1 seconds, so 20 times 0.1. All right, and that gives us 2 kilogram meters per second. All right, and that is how much momentum the ball has when it leaves the slingshot. So we use that actually as our initial momentum when we start off here. So we've got a ball. and it has a mass of 50 grams, which is 0.05 kilograms. All right, and we know that it has a momentum of 2 kilogram meters per second. It doesn't exactly require it in this problem, but I think it's good to figure out how fast that would be going. And so if you take the momentum and you divide it by the mass, you get 40 meters per second. All right, that's how fast it's originally going, is 40 meters per second. Then we have also on here a can that has a mass of 0.1 kilograms, and that can is not doing anything at the beginning. So then the next thing that we know is we can figure out here the total momentum on this side, P total, equals 2 kilogram meters per second. All right, if you add up the momentums there. So that means we know that on this side, P total has to equal 2 kilogram meters per second. I tell you in this case that the ball has bounced backward with a velocity of 10 meters per second. So on this one, we know that that .05 kilogram ball has bounced backwards and is going 10 meters per second in the negative direction, so we'll call it negative 10 meters per second. You can calculate the momentum there then. If you take 0.05 times 10, you get negative 0.5 kilogram meters per second. All right, and so we know the total is 2. And if it has to total up to be 2, then we know that this can, which is 0.1 kilograms, has to have a momentum of 2.5 kilogram meters per second, because it has to add together to be 2, and we know the ball has negative 0.5. All right, total momentum is 2. We got that from the I part of this, the initial part of this. All right, and then as a last step, you can take the momentum of 2.5 kilogram meters per second and divide it by 0.1 kilograms, and you get 25 meters per second. So V final in this case equals 25 meters per second. All right, so hopefully these problems have helped you to see kind of in general what the exam will be like. It's going to be a mixture of concepts and problems, so make sure that you're successfully reviewing in both areas. And as always, if you have any questions about these, make sure that you come in and see me before the test.